Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist in our unit electric circuit we will study potentiometer and will describe the circuit and working of potentiometer. The concept of potential gradient will be explained in good detail and we'll also solve few numericals for our examination preparation. Let's start. This yellow highlighted part is the primary circuit of potentiometer, and potentiometer is a voltage measuring instrument. AB is a wire length of uniform cross section, and in primary circuit current flow in this wire length produce potential in wire length, and unknown voltage is compared with potential coming out of wire length, and by that comparable balance wire length gives us the value of unknown voltage. During measurement at the time of balance, this galvanometer indicates zero reading, so these potentiometer type of voltage measuring instrument won't draw any current from measured circuit during comparison. So we say potentiometer acts like an ideal voltmeter of infinite resistance which won't draw any current from measured circuit. So they can measure true potential difference without any loading error. So they are better than any voltmeter in that respect. The key component of potentiometer is a long wire of uniform cross-section area. The wire material is an alloy, constantan or manganese, which have high resistivity and low TCR. A voltage source and a current limiting rheostat is connected in this series circuit, and current in this circuit is given as voltage divided by the total resistance of this circuit, internal resistance of source, current limiting rheostat resistance, and the resistance of wire length. Now flow of current in this wire length generate uniform voltage drop on wire length. The entire wire length AB have homogeneous wire material of uniform resistivity, and all through the length it got uniform cross section area, and if its L length got R resistance, then resistance per unit length is denoted by small r, and it is constant all over length everywhere. And in this primary circuit, when voltage supply current in this series circuit, the current and per unit length resistance product become voltage coming across unit wire length and voltage drop on 1 unit wire length at the time of circuit operation, where we balance unknown voltage with this wire length, is called as potential gradient. So we say potential gradient is voltage coming on unit length of this wire, and it is denoted by small x letter, and potential gradient becomes most significant operational parameter in potentiometer measurement. At the time of balance, when this primary circuit is comparing unknown voltage, it is neither drawing any current from external circuit nor supplying any current to external circuit, and in that case a single current flow path takes place from source voltage in wire length to rheostat resistance and source voltage. So internal resistance of source, rheostat resistance and wire length resistance form a series circuit. In this series circuit, applied voltage generate a current, and flow of current in wire length having uniform cross section area and identical resistivity all through the length. The resistance per unit length of wire is small r. Then the product of current and per unit length resistance become voltage coming across unit length of wire, and this voltage coming across unit wire length is called as potential gradient. Let's imagine that unknown voltage is compared with voltage coming across wire length, and this galvanometer is connected by a jockey contact at 3 length positions. One is L length, that we call balance length, another is L1 less than balance length, and the third one is L2 greater than balance length. So in first case, when wire length is L1 and voltage per unit length on this L1 length is potential gradient x, then L1 length got voltage XL1, and if unknown voltage to be measured is greater than XL1, then in this local loop of secondary measuring circuit there is an imbalance current flow, and that current in galvanometer indicate one deflection. And when this jockey contact is at L2 length, and from A to L2 voltage per unit length is potential gradient x in potentiometer wire, then L2 length have XL2 voltage, and let XL2 is greater than unknown voltage. Again the difference of two voltage in a local loop circulate a current, and this time the current got opposite direction in galvanometer, so the deflection of galvanometer get reversed, and surely there is a in between position. There exists a suitable L length where jockey is placed on wire, produce A to J position position wire length voltage XL such that that voltage become equal to unknown voltage, and in that case, due to balance of two voltage, there is no net loop voltage and there won't be any current flow in this loop. So this galvanometer indicate null deflection at center 0 position with zero current conditions, and this particular condition is known as balance condition of potentiometer measurement, and potentiometer circuit is used only at the time of balance. And in this balance condition, this primary circuit of potentiometer won't draw any current from this secondary measured circuit. There is no circulation of current in this local loop, and the same source current passes through potentiometer wire length AB and rheostat such that this primary circuit become a series circuit at the time of balance. And if we know potential gradient in this primary circuit, we can measure unknown voltage just by measurement of balance length on wire length, and product of potential gradient and balance length gives us the unknown voltage. At the time of balance, this primary circuit acts as a series circuit and current through all these elements is the same, and total source voltage divides among all circuit resistances, and voltage coming across balance length of potentiometer wire and unknown voltage become equal to each other, and there won't be any current flow in this secondary loop or in this galvanometer or series resistance or resistance connected parallel to galvanometer. So whether these resistance are there in the circuit or have different values, the balance condition in the measurement won't get changed by the change of these resistances, as at the time of balance no current flow take place in these resistances. So these resistances are in fact ineffective at the time of balance. So if you increase the value of resistance R1, this balance length neither increase nor decrease. We usually start our experiment with key K1 open and K2 closed such that both resistance R1 and R2 remains in circuit at the time of imbalance. They protect our sensitive galvanometer from higher amount of imbalance current, and when we during experiment comes very close to balance conditions, to increase sensitivity of measurement, we short circuit this R1 resistance by closing key K1 and we remove this R2 resistance by opening key 2, and we'll get more sensitive and safe result by this action. In laboratories to check proper functioning of potentiometer circuit, the jockey contact of galvanometer side is once placed very close to wire end A, and imbalance indication is obtained in galvanometer in one direction, and the same jockey connection when placed to the other end B, the imbalance current in galvanometer indicate opposite direction. So definitely there is some in between position in AB wire where galvanometer will show null deflection and balance condition, and we say this potentiometer circuit is in proper functioning. But if jockey contact at A and B at both positions indicate deflection in only one direction, then it means this circuit is not in proper functioning, and there could be two cases. In first case, when jockey contact is near A, imbalance in galvanometer indicate certain deflection, and when jockey contact is moved to position B, the imbalance deflection remains in the same direction and it will also increase. The cause of this problem is wrong connection of unknown voltage in potentiometer wire. The high potential end of source voltage connected to A is a high potential terminal, and we have to connect measured voltage in such a way that its high potential terminal should connect to high potential terminal A of potentiometer wire. Unfortunately, we have connected unknown voltage with wrong polarity, and in that case, in this local loop, unknown voltage and voltage of wire length both become additive together, and they added together produce imbalance current in galvanometer, and increase wire length voltage, and that increase imbalance deflection. So to correct this, we have to revert the polarity of unknown voltage, and its high potential terminal should connect to high potential end of AB wire, that is A. In second case, when our jockey connection is near A position of wire, galvanometer show a deflection in one direction, and when jockey is moved to position B, the imbalance in galvanometer decreases, but we won't get null deflection. Only amount of deflection has reduced, but the deflection is again in the same direction. It means the total wire length voltage from A to B got a lesser magnitude than unknown EMF. So we have to increase potential gradient in this AB wire, and that can be increased by increasing current in this AB wire, and that that is possible by either reducing this current limiting rheostat resistance value or increasing the source voltage in primary circuit. Before doing any measurement from potentiometer, we have to standardize potentiometer, and standardization of a potentiometer is a process of finding out potential gradient, that is voltage drop per unit wire length of potentiometer for the given primary circuit conditions of the potentiometer. And for standardization, we have to use a standard cell whose value is fixed and known to us, and for that we will use either a Daniell cell of EMF 1.08 volt or a cadmium cell having EMF 1.0186 volt, and standard cell is balanced on potentiometer wire length. First we connect primary circuit of potentiometer, an external source voltage with its internal resistance and a current limiting rheostat resistance is connected to AB wire length of potentiometer, and then standard cell is connected such that high potential terminal of standard cell is connected to high potential end of potentiometer wire, that is A, and then a sensitive galvanometer is connected to other end of standard cell, and other end of galvanometer is connected to a movable jockey contact that slides over potentiometer wire. And for correctness of circuit, when jockey contact is at A position and then at B position, then at these two conditions the galvanometer deflection should be in two opposite directions, and definitely in between AB length there is a suitable wire length small l, where voltage of AJ length become equal to this standard EMF voltage. We know voltage coming across unit wire length is potential gradient X, then across L length of potentiometer the total voltage is XL, and that XL is equal to unknown voltage E at the time of balance, because in balance condition this galvanometer shows zero deflection. That means this standard EMF and AJ length voltage is the same, so we can find out potential gradient as voltage on 1 unit length as ratio of standard voltage to corresponding balance length on potentiometer wire. Once potential gradient is obtained by standardization in a potentiometer circuit, its primary circuit parameter should not be changed, and if with the same primary circuit conditions a higher known voltage is to be balanced on wire length, then higher voltage will balance on higher balance length, and the ratio of voltage and balance length potential coming across unit wire length remains the same, because potential gradient is voltage across unit wire length of AB, and if resistance of unit wire length is small r and current flowing in this primary circuit is I, then potential gradient is I into small r, and resistance per unit length is given as resistivity upon area, and we can say potential gradient depends upon current flowing in primary circuit, and if all primary circuit parameters are same then current will remain the same. The resistivity of wire length AB and area of cross section of AB length both are constant, so we say potential gradient remains the same. So we can conclude the potential gradient is determined by secondary circuit voltage, but the value of potential gradient doesn't depend upon secondary circuit voltage. Higher voltage would have higher balance length, and the ratio of voltage to balance length remains the same, as potential gradient is solely decided by primary circuit parameter, that is current, resistivity and area of cross section of wire. The potential gradient of potentiometer, that is voltage coming across unit wire length of potentiometer, is given by these two expressions. One is voltage which is coming across L length produce voltage per unit length as potential gradient, and the second is product of current and per unit length resistance gives per unit length voltage, and per unit length resistance is resistivity over cross section area of wire. So we got two relation of potential gradient, one related to length and voltage and other related to current flowing in wire and area of cross section of potentiometer. Now these two relation looks very contradictory, and to obtain potential gradient we have to select proper potential gradient relationship for analysis purpose. When nothing about current or voltage is specified in our questions, then we presume that voltage across total wire length is constant, and we can use V by L relation for potential gradient calculation. If information about current is specified, then only we have to use IR or I rho by A formula. Otherwise, we have to use V by L formula for potential gradient calculation. Some example will explain this concept. In all these examples, we have to find out change in potential gradient. In first case, it is given that wire length is doubled. So nothing about current and voltage is specified. So we can presume that voltage coming across L length of potentiometer wire, that is AB, remains the same, and we can use potential gradient as voltage per unit length. And since voltage is same and length is doubled, so potential gradient will become half. In the second case, we have given that the diameter of potentiometer wire is doubled. We have to find out change in its potential gradient. Since nothing about current and voltage is specified, so we can presume voltage across L length of wire is constant and our potential gradient formula is V by L, and in this relation wire diameter has no concern, so potential gradient will remain as it is. In third example, it is specified that current and length both are doubled. Since current information is given, it become doubled, so we have to use potential gradient formula I small r or I rho by A, and in this relation length has no concern but current is given, it is doubled, so our potential gradient become double whatsoever the change in length has no concern in this calculation. In next example, both current and wire diameter are doubled. Since current information is given, so we have to use potential gradient relation as I rho by A. Double diameter will increase our area to 4 times, so current is doubled, area is 4 times, so potential gradient become half. In next example, current is constant and wire length is doubled. Since current information is given, so potential gradient is I rho by A, and in this relation length has no concern, current is the same, rho and area is also the same, so potential gradient will remains the same as L has no concern in this calculation. When rheostat resistance of primary circuit is increased, then it will increase total resistance in primary circuit, and that will reduce current in primary circuit, and reduced current will reduce potential gradient in wire length, and for the same measured voltage, reduced potential gradient will increase balance length. Similarly, when rheostat resistance is decreased, it will increase circuit current, and increased circuit current will increase potential gradient in AB wire length, and that reduce balance length for given voltage. The next numerical will explain this concept. In the primary circuit of potentiometer, a cell of EMF 2.2 volt and negligible internal resistance under rheostat of range 22 ohm is connected. That means rheostat resistance value can be changed from 0 to 22 ohm continuously. The resistance of 10 meter long potentiometer wire is 18 ohm. We have to find out minimum and maximum value of potential gradient in this case. We know potential gradient is voltage coming across unit wire length, and if unit wire length resistance is small r and current in primary circuit is I, then potential gradient is IR, and resistance per unit length of potentiometer wire of 10 meter length and 18 ohm resistance is 1.8 ohm per meter. Now for minimum potential gradient, the circuit current must be minimum, and for minimum circuit current, the primary circuit resistance must be maximum, and maximum value is possible when rheostat is fixed at maximum value 22 ohm. So the total circuit resistance of wire resistance 18 ohm and rheostat resistance 22 ohm become 40 ohm. So in primary circuit, 2.2 volt source voltage in 40 ohm resistance produce this minimum current, and resistance per unit length when multiplied by minimum current gives me minimum value of potential gradient as 0.099 volt per meter. Now similarly, for maximum potential gradient, primary circuit current should be maximum, and this can be obtained by minimum value of rheostat resistance, that is 0. So in that case, when rheostat resistance is 0, only potentiometer wire is there, then 2.2 volt produce maximum current voltage divided by only potentiometer wire resistance, and resistance per unit length is again 1.8. So maximum current and per unit length resistance produce maximum potential gradient equal to 0.22 volt per meter. In the primary circuit of a potentiometer, the wire got 10 meter length and its resistance is 10 ohm, and a source of 2 volt with 0.1 ohm internal resistance is connected with rheostat resistance, and it is found that a known 5 millivolt voltage balance on 5 meter length of this wire, then we have to find out potential gradient and series rheostat resistance value. So we know potential gradient is voltage coming across unit length and 5 millivolt come across 5 meter length. So voltage per unit length is 1 millivolt per meter, and that become our potential gradient. Now potential gradient is current multiplied by per unit length resistance, and per unit length resistance is 10 ohm in 10 meter. So per meter it is 1 ohm. So potential gradient divided by per unit length resistance gives me circuit current, and circuit current in this case is 1 milliampere. So circuit resistance is voltage divided by current, and the voltage of source is 2 volt, and current in primary circuit is 1 milliampere. So total primary circuit resistance is 2000 ohm, and internal resistance and wire resistance is respectively 10 and 0.1. When they are subtracted from total resistance, then the remaining resistance 1989.9 ohm is rheostat resistance in this case. In a potentiometer, L meter length of potentiometer wire has 20 ohm resistance. If primary circuit has a source voltage of 5 volt and a current limiting rheostat is connected in circuit and a standard cell of 1 volt balance on half of wire length, then we can find out rheostat resistance from these information. And if the same rheostat resistance is now doubled, then what is new balance length on the potentiometer for same standard 1 volt source? So in first case, when 1 volt balance on L by 2 length, then potential gradient is 2 by L volt per meter, and potential gradient is product of current and per unit length resistance. And in this circuit, source voltage of 5 volt with wire resistance 20 and rheostat resistance RH produce this much amount of current, and L length got 20 ohm resistance. So resistance per unit length is 20 by L, and when we compare the two, then 2 times rheostat resistance and 40 become equal to 100, and rheostat resistance by this calculation comes as 30 ohm. And in next case, when rheostat resistance is doubled, becomes 60 ohm, then the new potential gradient is new current multiplied by resistance per unit length, and L length got 20 ohm resistance. So resistance per unit length is 20 by L. The source voltage 5, rheostat resistance doubled to 60 ohm, and wire length 20 produce this much current in primary circuit. So our new potential gradient is 5 divided by 4L, and for 1 volt, if balance length is L, then measured voltage is potential gradient multiplied by length, and potential gradient is 5 by 4L. So balance length from this calculation is 0.8 L. So at 80% length position, now the same 1 volt get balanced as increased rheostat resistance has decreased current and potential gradient in this measurement. This informative learning video has explained the basic working of potentiometer in great detail. Now you know what is potential gradient and on which factor it depends, and you can also solve numerical which may be asked on potentiometer in our examinations. Our other learning video are equally useful, and you can use them in your studies and share them with your friends. And if you need our doubt clearing online classes and dedicated exam centric notes, do join our membership by clicking join button just beneath. Thank you very much.